All right, so let's talk about combinatorial proofs. This is our last concept, and it's a different kind of concept because it is literally about, like I said, it's about trying to tell a story. So this is for combinatorial, a lot of combinatorial identities. It's very common for solving combinatorial problems to show that something we're counting is actually something else we're doing. Um, a paper that I worked on with someone in grad school. It turned out to be we started it, a group of us. She took it further and turned it into her master's thesis. We ended up showing that a measurement that we were actually looking at turned out to be another key measurement. So we used kind of a combinatorial proof to explain why those were actually the same exact idea. So it's kind of this really cool idea and lets us attack it. So let's just jump into an example to get this idea going. So this is a proof that we have done. And as I said, as soon as we get started, there's Alejandro. Welcome, Alejandro. Welcome, Alejandro.
Oh, can you hear me?
I can hear you. Can you hear us?
Yeah. Let me mute.
Perfect. I was just teasing Cameron that as soon as we started, that's when other people jump in. It's like guaranteed every time I do one of these things, we start, and that's exactly when people jump in. So, what is a combinatorial proof? First off, it's really just telling a story. So, what we're going to do in a combinatorial proof, let me turn on my annotation notes. We're essentially going to tell a story. We're going to say, what is this left hand counting? So, we have the question of what is this counting? Come with an example of it. And then our question is the same thing. What is this one counting? And we're going to then show that they are this exact same thing. So let's just talk about for a second. Let's figure out an example of which of these do you all actually, let me ask you all, you two. We'll let Jackson, we'll have to watch it because he's not here, and then he can participate. We'll leave one problem for him to work on. But I want you two to, I want to ask the question of which of these do you think is easier to explain what it is counting?
The left side.
The left side. So Alejandro, what would you say the left-hand side, sorry, left-hand side, what would you say that is counting?
The sum of integers from 1 to n.
Okay, so sum of integers. Okay. The problem is this is pretty vague, isn't it?
I guess without the starting point to the end.
So tell me a real world situation where we're adding up integers.
Like any integers, like I mean, all the time, I
No, we're,
guess.
we're adding adding up all the integers up to n.
Oh, I don't have
When
no
when
idea.
would I do that in the real world?
I don't know.
And when I say real world, I'm being kind of loose in this. Okay, let's switch gears then. Let's talk about this right-hand side then. So in the right-hand side, what is it counting? What's it measuring? What is that number? What can we interpret from that number, that formula?
Almost like a square, but like one side's a little longer and we're taking half of it. I don't know.
Well, you're right. So in fact, I'm going to rewrite it this way. Can I rewrite this as 1/2 n times n plus 1? So what is this then taking? Let's talk about what is this really taking then? I like how you talked about a square. If we ignore the 1/2 for a second, let's ignore this 1/2. So let's ignore that and just focus on this. What would the square or this isn't a square, obviously, because they're not the same. What would that shape look like?
A rectangle.
Okay, so let's draw a rectangle. Okay. And how about I make this side n and this side n plus one, because I drew this side a little bit longer. But how much of this rectangle do I want?
Half of it.
I only want half of it. In reality, if you go back to anything else, it's actually where the formula of a triangle comes from, is you take a rectangle and you chop it in half. But this is great, but how is this a sum of integers?
No clue.
Well, let's start off. What if I do a box here? Can that box be a 1 by 1 box? If I come down all the way like this. And then can I make another one that goes right here? And another one that goes right here. And this is going to come all the way down. I know I'm gonna have a fixed number here, but I'm just kind of working with this. Work with me here. Be imperfect. So I'm gonna take these things and extend it all the way out. Two, three, four, five, six, seven, eight, nine, 10. So I have to go 9 this way. So that's 4, 5, 6, 7. Need to go 2 more up. All right, so I actually have a fixed number here, but it illustrates the same idea. I could have done a bunch of dots to illustrate all the parts that I don't really have, and I'm kind of missing in between here. So let's kind of look at this for a second. Oops, trying to erase my dots. Erasing whole lines. All right, let me come back and get my lines back in. So are you two okay with this? We really only want to find the area of half this thing. Now, one way we could do the area is literally cut it vertically down the middle or horizontally, depending on if n is odd or n plus 1. Because if n is odd or even, if n is even, I can cut it horizontally. If n is odd, n plus 1 is even, so I can cut it vertically. But let's not do that. So let's pretend that diagonal that I kind of mentioned. But let's look at the diagonal values. So let's look at the diagonal squares. And for this, I'm going to change colors. I'm going to switch over to red. Are either of you colorblind?
No.
I don't think so.
And I'm going to do a highlighter. So if I fill these diagonal ones, I fill a bunch of diagonals, I just keep going down a diagonal, you'll actually notice that it doesn't actually hit the far corner. Why not?
It's +1.
Yeah, so because it's not perfect, I don't want that one. Get rid of that last one. But let's look at this. The red dots, so let's look at the first row. How many red squares do I have in the first row?
And
red, and so let me do in this row right here, how many red dots do I have? I don't have n in the first row. I only have one, right, Alejandro?
Yeah,
How many's in the second one?
2.
Three.
Two.
So wait, what is the total sum of all the red dots equal to?
It'd be 1 + 2 + 3 + 4 all the way.
In this case, it's all the way up to 9, but it let's say could Cameron, can you see how that would actually go up to 10? So if I start by just adding up all those different sums, I get a triangle like this. Now, if I take that triangle and I flip it and add it to itself, I get a rectangular area that actually works quite well. And the reason I couldn't have just done a triangular values because the original thing was all those step values. And so that threw off if you tried doing an actual thing. So let me kind of illustrate this. Can you guys see how the red squares, the red dots, I should say, the red dots actually equal, let me get my spotlight, this summation that we were already talking about, the left-hand side. But if I take those red dots and take them and I flip them and add them back to themselves, I get an n times n plus 1, but I only need half that because I doubled it. And so that's actually how we get the right-hand side. Tell me what you're thinking right now as you're seeing this problem.
To me, it makes sense that they're both counting the same thing. I can see the pattern in half of the or the in the half of the rectangle to be the adding of integers, so that makes sense to me.
Okay. Alejandro?
I think I'm right there with her.
Okay, so you guys are feeling good about this one.
Yes.
All right, so let's move on to another one. I want to count this. So again, let's do the same thing. Let's talk about what I could be counting with either side of that. So you can start with the right-hand side and say, what is that counting? And don't just be like, it's 2 to the nth power. What could 2 to the nth to the n be counting?
The number of times to doubles something or something along those lines.
Number of doubles. Yeah, it could be if you're doubling something, how many doubles?
Like how many pairs or something, maybe?
Well, it wouldn't be pairs because pairs wouldn't work out. Let me ask you a combinatorial question that I think you can quickly see where I'm going with this one. So consider for a second if I made a binary string, so that is a list of binary numbers of length 5 right here. So that means this first number right here could be 0 or 1. This second number could be 0, 1. Third number could be 0, 1. Fourth number could be 0, 1. Fifth number could be 0, 1. How many possible binary strings of length 5 are there?
2 to the 5.
Okay, so this is 2 to the 5th power. So what could this right here be counting?
How many possible combinations there are of binary or of length n?
Yeah.
Maybe?
So we just write this is number of binary strings of length n. So over here, let's deal with this in terms of binary strings. So we're dealing with binary strings of length n. The question is then, what on earth is this? What would n choose 1 be? What would we n choose 2 be?
It's a good question.
So take a minute. I'm not in a rush. This is why combinatorial proofs are challenging, because you have to stop and think, okay, let's pretend that we're living in the binary string world. In reality, I just create binary strings, just one example of where you have 2 to the n, something that's like this. It's often things that are, you have 2 options, you're picking any 2 of them, and then they're in some sequence. And repetition is allowed. So that's why we have this whole 2 to the 5th power. So let's think about that second. Let's just break this down first. What would be n choose 1? I'm not asking the
And
numerical value, but what would that be
oh,
possibly counting?
That how many ways there are to choose just one of whatever string you have?
So I like where you're thinking. What are we choosing for that string?
is it a 0 or a 1?
Okay, so in this case, could this literally, I'm trying to get you all to think of this way. This would count the number of binary strings with 1, 0. Why would that be the number of ways to count binary strings with 1, 0?
Because you can choose which like slot of how many and like which one has 0 and then the rest are retrievable with anything.
Then with that in mind, what would n choose 2 be?
Number of strings with 2 zeros.
Yeah, and the reason we have to do a choose situation is it doesn't matter if we picked 1 and then we picked 2. That's the same thing as we picked 2 and then picked 1. So the order of what we choose doesn't really matter. It just matters that we pick those objects. So then what is this? Let's break it down then. What is this left-hand side? What is that counting?
Is it all the possible? mm, all the possible strings of
Yeah,
length
so we can
n?
break it down. This starts with all the binary strings of length n that have 1, that have I zeros, where I ranges from 1 to n, which is all the possible which is all the possible values of zeros. So if you go through all the possible I can have 1 0, 2 0, 3 zeros, all the way up to all zeros. Doesn't that account for all the possible situations that we could have for this?
Yeah.
It actually isn't. There's one thing that I missed in writing this proof. It's, and I just realized it as I was looking at it. This number right here should be I equals 0. Why would it actually start with I equals 0?
All ones.
Yeah, what if it's all ones? That I have to count that situation. And then I have to count if there's all but one, all but two ones, and so forth. Let me do this totally different. So I do with binary strings, but let's do this totally different. So I'm going to take you back to combinatorics. I mean, and when you guys first ever learned about set theory, so if I give you, so I want to take it back to sets. So I have a set, and we talked about power sets. What is the power set of a set?
Set of all subsets of S.
How many subsets of S are there always?
Is it 2 to the end?
Why are there 2 to the n subsets, by the way? Besides, that's the formula that everyone talks about.
It's all the possible, like if you have n elements, you can either have all or a certain amount of one of the elements in it. So it's like binary to 2.
Yeah, because it's a well, you're right. It's a Boolean decision. Take each and every single element, and either it is in the subset or it's not. And so you have n things, each of which have 2 options. So we have 2 to the n. That in mind, what would the left-hand side of this? Because going back, this terminology right here is often used to talk about something specific. If you look at most textbooks, and again, that should be a 0 right there. N choose I or N choose K, whenever they have this, they usually say this equals the number of what? Well, what was this just counting?
Two to the
Like
end
in
is the
terms of
number of binary strings of length.
Well, binary strings, but what did we just talk about just now talking about? This actually counts. We just said this also counts what?
the number of subsets in your power set.
So what could this count in terms of subsets?
The number of ways to have like a specific element in all the subsets or something like that.
Let's say size instead of cardinality. Isn't this counting how many subsets are of size I? Let me just do an example real quick. So let's take 5 choose 0. What is 5 choose 0?
So 1
So it
or
turns out
is
that
it 5?
this is 1. This is exactly 1.
Oh
Because
yeah, there's yeah,
what are the subsets of size 0?
it's just the empty.
The empty set's the only thing of size 0. It's the only thing in all of set theory that is of size 0, cardinality 0. So we have this plus What's 5 choose 1?
All the subsets that have one element.
And of course, there's clearly going to be
5.
5 of them because you just pick each and every single one of them. So this is going to be 5. And then you have 5 choose 2. Which happens to be 10. How many pairs can I pick out? So this is going back, and then I can have 5 choose 3. How many triples can I pick? Which ironically is the same thing as 5 choose 2, because again, the opposite of choosing what I want is choosing what I
Don't want.
Yeah, and we all do this sometimes. I mean, I don't know if I often say this in class, and I don't know if I said this to y'all. Have you guys ever been like, I am not going to, I'm not, I don't want to eat that, so I'm going to exclude that first? Like you walk up to a buffet or something, the cafeteria, and you're like, hey, what are my options? And you look around, you're like, that's Brussels sprouts. I do not like Brussels sprouts. Take that off. Have you just removed one thing?
Yeah.
It's the same thing as if I'd walked up and said, I want everything. So saying I want everything except Brussels sprouts is the same thing as walking and saying all I want is Brussels sprouts. In terms of counting how many ways we can do something. And that's actually, by the way, I just gave you a combinatorial proof of why n choose k is actually equal to n choose n minus k. Because this is choose what I want. This is choose what I don't want. And those are the exact same count. You both are being really quiet. And because I don't have any visual tells, I'm just double checking. You guys feeling good about this?
I think so.
So interesting enough, this is equal to 10. What, Cameron? Sorry.
I just said I'm following, but just kind of.
All right. And then if I go through the rest of these, 5 choose 4 and 5 choose 5 are also going to be 5 and 1. If we add these up, just so you can really see this, this turns out to equal 32, which is 2 to the 5th power. So we essentially talked about for this problem 2 different combinatorial proofs. One using binary strings, and a second one talking about number of subsets of a set. So what's the general theme that you're getting on these combinatorial proofs right now? Before we move on, what's a common aspect of them that you're seeing, and also what's a challenge that you're seeing?
That you have to kind of assign like a real life situation to it.
Mm-hmm. Doesn't really have to be real life, but you have to find some kind of concrete situation to tie it to.
I think my downside is being a little rusty, but
And this is where combinatorics comes back to play a huge role. And by the way, this strategy of combinatorial proofs is only used in combinatorics. Similarly, something we didn't even talk about is like trying to do epsilon delta proofs. If you're ever doing real analysis, and I don't mean like here, we kind of start off with some really simple real analysis. As you get to like graduate level real analysis, where you have tons of limits and all those multi-dimensional limits and so forth, there's a joke that for any, if I'm doing a proof in analysis, my first step is say, let epsilon be greater than 0, and then we move from there. In combinatorics, there's a whole bunch of different strategies. We sometimes use induction. We use proof by minimum counterexample. We use combinatorial proofs. We use a lot of these different things. In number theory, you guys have seen a lot of things where you're just kind of like, if it doesn't feel like you're just kind of pushing the numbers around, but you're really just doing nothing. Have you felt that way
Yeah.
on some of these problems we've done?
Yeah.
Yes.
That manipulation, that's a very common thing in number theory, though advanced number theory tends to then rely a lot more on past concepts, and using some different things. So these things are interconnected. It's really crazy. Like there's a classic theorem in number theory called the Chinese remainder theorem. The proof of the Chinese remainder theorem tells you how to find it. So the proof actually includes the actual algorithm that you use for the Chinese remainder theorem, but the actual theorem only tells you the existence of something. It's kind of weird. So, but to prove it, we prove by finding an example of existence. And that's kind of the point, is that we can, to show a solution exists, we have to find it. Rather than just saying, it could exist. Well, that's pretty vague. We actually then are just taking a step further. So let's continue this combinatorial proof kick though. I'm gonna leave this one actually. This one's a fun little one. And sometimes people call this the this, I wrote it, I didn't write it down, and so that's my fault. Um Darn it. What's his name? It's a French guy.
Pascal?
Yeah, it's Pascal. So sometimes people call this a Pascal identity, because if you look at the Pascal triangle, I knew it was French. I've dealt with too many French people lately. Um, 1, 2, 1. What's the next row in this? And how do you know that? Do both of you know what the next row of Pascal's triangle would look like?
It's like 146.
How do you do that?
You add the two number or integers on top.
So for this one, I take that number and I go up to, hypothetically, there's a 0 hanging out here on the outside, right? So I'm going to take this one, I'm going to do 0 plus 1. That's going to give me 1. 1 plus 3 is giving me 4. 3 plus 3 gives me 6. 3 plus 1 gives me 4. And again, we do a 1 because there's a 0, an imaginary 0 hanging out there. Well, the interesting part is that actually, if you think about it, that fits perfectly for this identity right here. But that's only saying this identity works because because this really cool Pascal's triangle exists. Well, the problem with the Pascal's triangle is it's built to be that, have that property. So you have to then explain how this is actually counting each thing inside of the tree. And even then you're still kind of leaning. The truth is that Pascal's triangle is all based on the binomial coefficient. So, pardon me, it doesn't quite work. So let's take a break for a second. Let's go back to the example we were just talking about, because I'm going to leave this. I'm going to leave this for Jackson, and you guys can work on it too. But I want to give a hint right here to get started. We talked in the last problem about what this could potentially be counting. What does n choose k count?
The number of, like, in terms of subsets or
Sure,
in general, or
sure. In terms of subsets.
if you have n elements, how many of them how many subsets can you have of length or cardinality three, wherever the or K,
Okay,
something
okay.
like that.
Yeah, so it's how many ways can I have it of length K? Hmm. So we're talking about elements, subsets, and so let's think about this. What's the difference then between n choose K and n minus one choose K?
Get rid of get rid of one of the total elements.
Oh, okay. So that's kind of the hint, and you guys can play with this. I'll put this on this video and up. You guys can work on it too. That's kind of the idea. So once we start thinking about subsets, we're gonna like, okay, wait, this is the counting subsets plus more subsets. Well, why would it equal the sum of subsets? Remember, if you're counting things, you're adding them, you really want them to be disjoint. So I would need this situation right here to be this to be a separate situation than this. In other words, there's no overlap. Otherwise, we have to do the whole principle of inclusion exclusion. We're just going to say they're completely disjoint. So we kind of have to leverage that. Let me do a one harder one though. And this one is kind of hard because it's not one that is easily seen. So let me ask a quick question of what would you say that this is counting? I want you to look at these numbers, all these really crazy formulas. What do you think this is counting? Pick a side and tell me what it's counting.
Stumped.
Say again, Alejandro.
I'm stuck.
Okay.
I
Cameron,
think
you got any ideas?
yeah, so I think I'm guessing the left side because of just like n choose k. If n choose k is the number of subsets of cardinality k, that would just be the number of subsets cardinality k squared. And then
It would be.
the other side is you just I don't know how to say, I don't know how to word it, but like you would double n, which is I guess the number of elements you have, and then just choose n. But I don't know how to put that into words, really.
Well, you're right about that's what those numbers are. So let's think about this for a second, because I'll be honest, I played with this over the last couple of days, and this was on a list of problems I had, and I had to stop and think for myself. I was like, wait, what could these things be counting? I started with the left-hand side. If you ever see a number squared, what is your instinct that that is counting?
Like in terms of like area or something, or
Yeah, how often when you see something squared is it talking about area?
pretty often, I guess.
Okay, that's very, very common. I think that's a natural thing. That was where my brain went first initially too. I thought, wait, this seems like it's an area problem. I was like, but that doesn't fit. And then I had a thought about the right-hand side, and I remembered a problem that I had done years ago. Um, I did a much more complex, but this came to my mind. So I want you to imagine for a second that I have a grid. So again, let's just create a grid. All right. So this is a grid that's 1, 2, 3, 4, 5, 6, 6 by 6. All right. So I'm going to start right here in this. This is my start. Yeah, y'all okay with that?
Yeah.
And let's suppose this is
Yep.
my end. And let's suppose these are city blocks. I'm trying to move from the start to the end, which means I can't kitty corner across any of the blocks. I got to go down and I got to go up and so forth. There's only two directions I can go. I can either go, I can, I can go one of two ways. One is up or two is to the right. So I'm saying I can't do something crazy like I'm gonna pick a different color. I can't be something where I'm like up, up, down, over. No, no. A, because that's not efficient. Does that make sense that that's not efficient at all to go back down after I go up?
What if the road's closed?
Well, we're supposing all the roads are open. Dang it. I just undid all that. Sorry about that. Let's oh, good. Whew. It's close. All right. But I lost it. Okay, so how many ways are there? So let's think about this. If I'm going from here up to here, how many ways are there to start and end if all I can do is go up and go to the right? How many total steps do I have to, how many total blocks do I have to traverse? And how many ups and how many rights are possible?
Well, there would be a lot of combinations of ups and rights, right?
But let's talk about the total number of ups and rights that are possible. Whether I pick a path that goes like, let me choose an, again, red, so it's standing out. Whether I choose, all right, you both okay with this path that just comes up and goes all the way over here?
Yeah.
How many blocks up did I go? How many blocks to the right did I go?
Uh,
5 and 5.
So did I move a total of 10 with 5 up and 5 to the right? What if I take this bottom route where I go all the way to the right first and then up? How many total? How many up? How many right?
That would be the same. 5 and 5, so 10.
Okay. What if we take, let's do a crazy different one. This one doesn't seem to fit any pattern. How many total blocks did I traverse? How many up? How many to the right? You can literally count them.
Five and five.
Why?
You
Why
can
is it
only
that,
go up.
go ahead, Alejandro, sorry.
No, I'm sorry.
No,
You can just go up and right.
okay, and so why do I have to guarantee to always go up a total of 5 ups?
If you don't, then you'll never, like, even if you went straight right, you won't be able to get all the way up if you don't go 5 up.
Because I always have to end up with 5 ups and 5 rights in order to get all the way up and over. So then what is this number right here on the right-hand side counting?
If you have a grid that's squared, the number of ways to get to the start and end, I'm just spitballing.
Yeah, if we're just assuming that we're starting down the bottom left corner, using only ups and rights, it's the number of ways to do those walks. Are we okay with that?
So would this not be the case if it was like a 5x6?
No, if it's 5 by 6, you're going to get a different value. So we're supposing that start and end are perfectly n by n grid. It's the only way this works. If you go an n by m grid, Alejandro, it does actually make it it's a slightly different formula. But it's actually not that bad. Instead, then the only difference is this top formula would be m plus n, choose n, where these are the rights and these are the ups.
Did you
Is what I'm
do
going to end up
m plus?
having. Go ahead. Sorry, I cut you off.
I was gonna say then, can you do m plus n, choose m?
Yeah. That goes back to the identity that we can just pick the other thing. Because if this is a total of m plus n moves, are you okay that they're my moves? This first one, it can be an m. Sorry, it can be not m. I could make this one up, right, 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 up. So I'm really picking in the sequence of moves because there's going to be m plus n moves or 2n if it's perfectly square. I'm picking which of those moves are ups. And then the remainder have to be rights. So I'm just going to stop right there. Does that make sense as to what we're counting on the right-hand side?
Yes.
Okay, then what on earth could the left-hand side be counting? Why has it got a square? That doesn't, we're not counting area, we're counting number of ways to walk. What do you think?
Since if we have n and k, I don't know what the analogy would be, but we just consider one side instead of 2n. But I don't know how we would go. Yeah, I don't know.
Okay, so wait. So are you okay? Let me go back to the 2n situation. Are you okay that if we have a sequence of moves, how many total moves do we have? Total.
2n.
2n moves. I like that. Could I break this into n moves and then n moves?
I guess.
Well, so what I'm saying pretty much is, could I do something like this, where I break it up and I say, I'm gonna give myself some ellipses in here. Um, dot dot dot, where this chunk right here is the first n, and this chunk right here is the second n. So in that case, let's just think about what would n choose k. If we're talking about the first n, what could n choose k tell me about the first n moves?
The number of ways to go a specific direction.
Yeah, so what if I said that n choose k is the number of ways to choose k ups in the first n? Would that make sense for n choose k? Wow, you're both being really quiet. I don't know if I just totally burnt out your brains or I lost y'all.
I think both.
Okay. So what I'm saying is this can count the number of K ups in the first N moves. I'm gonna go ahead and erase my grid now, just because I'm instead of having the grid, I'm gonna illustrate this with the sequence instead. All right, so let's do an example. Let's do a very specific example. Let's do an example. Let's suppose that N equals 4. So we have 4 moves here and then 4 more moves. Are you guys okay with that? We're going to split it up.
Yes.
So Cameron, pick any number from 0 to 4, and that's going to be how many ups we're going to have in the first chunk.
Let's do 1.
All right, where do you want to put that 1 up in this first grouping?
You can put it in that second slot. That's fine.
Okay, so we can put an up here. That means these other 3 have to be rights. Are you okay with that? Now, that was one way we could have done that. Are you both okay with that? How many ways could I have picked 1 up among those 4 different spots?
It'd be 4, choose 1, right?
Yeah, because again, we're just choosing which of the spots get an up. 4, choose 2 would be pick 2 spots, those get an up, everything else gets a right. Now, here's an interesting little fact. If I have 1 up here, how many rights do I guaranteed have to have? Or I should say, if I have K ups, how many rights do I have to have in the first N?
N minus K.
Yeah, because don't we have to fill the rest with rights? This accounts for N choose K. Are you both okay that this accounts for N choose K? Not N choose K squared, but N choose K.
Yes.
Okay, so the problem here is, what is N choose K squared? I'm just going to pause for a second. What's another way to write N choose K squared? Going all the way back to your algebra days, what's another way to write this?
N choose K times N choose K. Or
Okay.
like
Yeah, I like that actually. That's exactly what I'm trying to go, Alejandro. And we just said that this first N choose K is the number of ups in the first N moves. Are you okay with that?
Yeah.
What then is the other N choose K?
Right.
Well, over here on the right-hand side, what would N choose K? What I still have N spots and I'm choosing K, but what are there K of now over on the right-hand side? Guaranteed.
There have to be 3 ups.
Well, we have to have over here, if I have K ups, I now have to have N minus K ups. Because don't the rest of my ups have to be over in the second grouping?
Yes, that makes sense.
Then how many rights do we have over here?
Okay.
So this is really counting in the first N. I can have 0 ups all the way up to N ups. And then I'll have the same corresponding number of ways to pick the second N, but all the rights. So let's talk about this. Where could I put the rights over here in the second spot? If we put the up right here, if we had this particular sequence right here, how many ways can we still mix up the second grouping over here to have 3 ups and 1 right?
Or choose one.
And do you see how they are independent of each other?
Yeah.
Meaning how one's going to occur and then the other one's going to occur. And for each one of these options, there are still that many options over for this side.
Yeah, I think so.
So can you now see how this binomial identity is really counting the number of paths going from that starting point to the ending point on an n by n grid?
Yes, it makes sense. I just don't think I would have got there by myself.
And to be honest, this is why I don't often assign these kind of problems. I remember the first time I learned them, way my advisor kind of taught me to do this a lot more, and I did a little bit of this in my undergrad combinatorics class, but most of this came during grad school, was you have to kind of think about them almost like balls and boxes or walks. There's a lot of different things, and as you start working through a lot of different application problems, you actually build up a repertoire of then things to use for these binomial coefficients. I mean, for this combinatorial proofs. And to show you why combinatorial proofs are so beautiful, could we prove this without a binomial proof? I mean, without a combinatorial proof, sorry. Because in number theory, what would we normally do for this thing over here? How do we prove this normally in number theory? Well, let me just frame it. How would you normally solve this using any other method that you have? Pick all the other
Induction.
tools. Induction. Okay, so induction, we'd have to show this is true for, so we have a base case. What will be my base case for this one?
0.
So we have n equals 0, and then obviously the sum from 0 to 0 of n choose, 0 choose k squared equals, well, 0, which happens to be 2 times 0. I should make them equal, but this equals this, which is also 0. So therefore, they're the same. So base case, super easy. What is the induction hypothesis on this one? Either one of you. And this, I'll end right here. I know I've taken the full hour.
I think it's
I-
like k equals.
Yeah, suppose for n equals k, I know I can't do a k because I'm using a k. N equals j. The sum from k equals 0 to j of jk squared equals 2j over j. Now let's do our induction step. Consider n equals j plus 1. So we need to start with one side. Normally start with the left-hand side. That's just the way most people do it. We have k equals 0 to j plus 1 of j plus 1, choose k squared. Okay, how would you affect this and change this?
Break apart the sum.
Okay, you break apart the sum. What would this sum become? What could you how could you break apart the sum?
All the way up to j.
Ah, but what's still here in the binomial being squared?
It would be j choose k.
No.
J plus 1.
Because while we broke off the j plus 1 term of the summation, that did not change this value. You see how that value is not actually associated because each term is a k value. This is a k when k equals j plus 1, not when the overall value is j plus 1.
Yeah, I think that one almost got me on a previous assignment we had.
Yeah. And so you'd end up with this would be j plus 1 over j plus 1 squared. Okay, this is super easy. This one's just 1. But I still, oh, darn it. So this is where combinatorial proofs are much more beautiful because induction doesn't quite work. You would, if I was to attack this problem with induction, I would then have to use like the identity, honestly, in the previous slide, and I'll go back and show it, where I can change from the j plus 1 situation down to the j situation by breaking that into a sum. And then I could actually accomplish this. But it still becomes, so you could do this using that, but you have to then utilize that other identity and really, really leverage some things to your advantage. So the truth is combinatorial proofs, while I know the hard part of combinatorial proofs is coming up with that thing of what am I really counting? And even when I was going over this, trying to prep for this problem, just like I said before, my instinct when I saw the squared was that's counting area. I was like, wait, no, that's n choose k times n choose k. And then I said, okay, how could I break up the two n steps? And I sat there and I played with it, and then my brain started figuring it out. It sometimes just takes time to play with these things. This is why they're among the most complex, and I only introduce them usually in this class at the very end or in like combinatorics and graph theory when I teach that, because it's a combinatorics class. It's one of the strategies we use to prove a lot of our high level identities. So I hope that helps. I'm going to post this video. If you guys want to still tackle this and post your answers, you're welcome to. You don't have to. I will leave that for Jackson as part of his assignment, because you both were sitting here participating, and it is a challenge. I get it. This is totally hard. But this identity, how could you prove it? Remember we talked about this being subsets. How could I count this? What kind of subsets is this counting versus these counting? And we can go from there. Good luck. Thanks for all you guys have done. Go back. Are there any homeworks you still want to correct? Otherwise, I wouldn't. Otherwise, you're done. I think you guys have submitted everything, done a great job, and I appreciate all of your efforts this semester. So, anything I can do to help you all out? Let me stop recording. I don't need to record this anymore.